Now we're going to talk about the normal curve. So we use a normal curve to model continuous random variables that are normally distributed, which means that they are symmetric and bell-shaped. And remember, we talked about these sort of when we talked about histograms, and the histogram for something that's symmetric and bell-shaped looks something like this. So when we have a continuous random variable that would have a histogram that looks something like this, this is where that bell shape comes in. And remember, it's symmetric because the mean is right smack in the middle, and if we fold down the mean line, which I didn't get this perfectly, but if we fold down that mean line, it should match up on both sides. So a normal curve satisfies both of the requirements of a probability distribution. Remember, all probability distributions, regardless, have to satisfy those. So the area, and this should really say under the curve, equals 1. And each probability is between 0 and 1 inclusive. Or, if we look at the height of the curve, the height is greater than 0. Greater than, or equal to 0. So normal density curves, which is what that bell-shaped thing is, have several properties, and every single one of them will have this. And we've already talked about this. It's symmetric about the mean. And the mean is the population mean, because remember, these are considered populations. When we have a normal curve, the mean, the median, and the mode are all equal to each other. And because of that, the graph has one peak, and the highest point is at the mean, median, mode, since they're all the same. The total area under the normal curve is 1. The area under the normal curve to the left of the mean is 0.5, so half of it's to the left, and half of it is to the right, which makes sense because it's symmetric, right? So if the whole thing is 1, 0.5 has to be to the left of the mean, and 0.5 has to be to the right. So as x increases without bound, meaning it gets larger and larger and larger and larger, the graph approaches but never actually touches the horizontal axis. And as x decreases without bound, meaning it gets smaller and smaller and smaller and smaller, the graph also approaches but never touches the horizontal axis. And again, that makes sense because of the symmetry. So whatever it does going farther and farther to the right, it has to do the same thing going farther and farther to the left. So the empirical rule, and if you forget what that is, that was our 68, 95, 99.7 rule. So go back to section 3.2 notes on page 3. That can be used to estimate certain areas under the normal curve. It's not exact, but it's close. So remember, 68% of the area under the normal curve is between the mean minus 1 standard deviation and the mean plus 1 standard deviation. In other words, within 1 standard deviation on either side of the mean. 95% is from 2 standard deviations below to 2 standard deviations above. And 99.7% of the area is between the mean minus 3 standard deviations and the mean plus 3 standard deviations, or within 3 standard deviations of the mean. So what does that actually look like? Well, let's see. There's a couple things we have to know about what happens if we change the mean and the standard deviation. So if we change the mean of a normal density curve, it moves the graph along the horizontal axis. So changing the standard deviation changes the height and the spread of the graph. So now let's see if I can manage to actually graph these. I usually have the worst time. Well, drawing a straight line to start with would be helpful. Here is our horizontal axis. And we usually don't bother too much with the vertical axis on these. So if we graph a normal curve with a standard deviation, with a mean of 0 and a standard deviation of 1, it'll look something like this. And it keeps going and it gets closer and closer to the axis, but it never gets there. It's hard to draw that right. So there's our mean of 0, and here's our standard deviations of 1. So 1, 2, 3. We have -1, -2, -3. So that one is mean equals 0 and standard deviation equals 1. Now, if we graph a mean of 3, so different mean but the same standard deviation, 4 standard deviations, 5 standard deviations, 6. Our curve just moves along the axis. So its high point is going to be at 3. And let's see if I can draw this. So it's going to look, and I can't. Told you I have the worst time drawing these. I may get it right this time. If I can prevent my hand from... There we go. Close enough. So this one you can see has a mean of 3 and the standard deviation is still 1. So the two curves look exactly the same, except one is shifted horizontally along the axis. Now let's try to do it with different standard deviations and the same mean. So this time we have our horizontal axis with a mean of 0 and different standard deviations. 3, 4, 5, 6, and -1, -2, -3, -4, -5, and -6. So the first one is going to have a mean of 0 and a standard deviation of 1. So it's kind of going to look like this. Oh dear Lord. I'm telling you, these things aren't easy to draw. That's better. We'll go with that. So that one is our mean is 0 and standard deviation is 1. Okay, what happens with a mean of 0 and a standard deviation of 2? Well, the same thing kind of happens, it's a little bit different. So what happens is it gets flatter, so it kind of goes like this. So that one is our mean of 0 and standard deviation of 1. So the bigger the standard deviation, the shorter and wider it gets. So greater sigma means shorter and wider graph. And smaller standard deviations mean taller and narrower. This should make sense to you because remember, the standard deviation is how spread apart our data is. So the more spread it is, the wider the graph should be. And because the area has to stay equal to 1, if it spreads wider, it has to get shorter in order for that to stay equal to 1, the area underneath. So now that we've talked about that, we'll talk about what the area means in the next video and how to actually interpret it.